So good afternoon. Last time we have tackled on transmission line basics or the basic concepts regarding transmission line theory, not only on metallic transmission media but transmission line in general. And we've also discovered that transmission lines do not act as normal, just plain normal conductors at high frequencies. No? So for substantially higher frequencies, ingani ng equivalent circuit sa itong transmission line. Dili na siya plain set of conductors only, but mag-exhibit na siya og kaninga parameters na siya not only na siya resistance, but naasad siya kuan but naasad siya inductance, capacitance, and conductance, G, in between sa lines. So we could use this as our equivalent circuit of a pair of transmission line at higher frequencies. So these parameters, R, L, C, and G, are what we call primary electrical constants, and they are primary sila not only because they will be used for further calculations, no, meaning other parameters na atong pwede measure or calculate can be derived based on these constants. But also because mo gini ang mga primary na mga parameters that are very important. And also because napoy tayo ginatawag na secondary electrical constants, which are derived directly from the primary ones. So the secondary electrical constants, the most common ones and useful for our immediate discussion, is the characteristic impedance and propagation constant. Na-mention na ni Kadyot, I think, ang characteristic impedance last time. Wala ko dumdum na ako gini-expound further. So siguro ma-expound further today. So kato, no, kaning RL, C, ug G mo ning conductance, mo ning primary electrical constants, and ang secondary is ang characteristic impedance and propagation constant. Resistance and conductance are measured in conductance mo, no? So opposite sa ohms, resistance in ohms, per meter. Kaning upat, they are measured in per length, no? Usually per meter. So ohms per meter, henries per meter, farads per meter, and sabay kuan sa conductance, moles per meter. Okay. Inverse. So the characteristic impedance, as what I've said, this is not dili na siya resistance or impedance nga atong ma-measure using a ohmmeter. Dili siya, it's not an impedance or resistance just like that. And yes, dili siya mag-depend sa length sa transmission line. No? For example, coaxial cable, any length of coaxial cable, whether short or long, has a constant value, I mean, for a characteristic impedance na nasa sa mga 50 or 75 or 100. So mas yun sa kataas. So characteristic impedance or surge impedance is the ratio of the amplitudes of voltage and current of a single wave propagating along the line. That is, the wave traveling in one direction in the absence of reflections in the other direction. Wala siya somewhat like this, no? Example. So transmission line, ang manang travel nga voltage along the line, manang travel nga current, yan na. So, example lang. So voltage, current. So the ratio daw of the voltage and current at this point, constant na siya at any point. That is the characteristic impedance. Alternately and equivalently, it can be defined as the input impedance of a transmission line when its length is infinite. We could also define characteristic impedance ZO is equal to the input impedance of that line when the length is infinite. Characteristic impedance is determined by the geometry and materials of the transmission line and for a uniform line is not dependent on its length. So that's how we define characteristic impedance. So name pa lang daan, characteristic impedance mo na ang characteristic sa line mo na ang mag-define sa iyaha. Analogously, malagod yapon katong beta, no? Masyag beta sa atong BJT before. So mo na iyang characteristic. So mo na iyang formula, no? ZO is equal to square root of R plus J omega L, where J is square root of -1, no? Imaginary number. Omega is 2 pi F. Of course, we already know this one. Radial frequency, I think. So R plus J omega L over G plus J omega C. Kaning upat, muna isla katong naa sa primary electrical constants. Primary electrical constants. For extremely low frequencies, in the range of hertz to kilohertz, we could use this approximation. No? Square root of R over G. So omega is a very small value such that may mong negligible ang mga complex na components. And also, balipod if for extremely high frequencies, for which compared to the inductance, the product of the inductance and the frequency, layo ra ang R ug G. Sila na po ang make negligible. So for extremely high frequencies, the characteristic impedance is equal to square root of L over C. So that's the characteristic impedance, one of the secondary electrical constants. Another one is the propagation constant. Okay, so this measures the rate. This defines the rate of attenuation of the signal experiences as it travels along the line. So propagation constant, this may be useful in more complex calculations. I don't think nga maabotag iyan complex na ito sa mga calculations today. But ato lang i-define this afternoon nonetheless. So propagation constant determined or defined by the Greek letter gamma is equal to square root of the product of R plus J omega L and G plus J omega C. Product kani kay quotient. Is also equal to alpha plus J beta. At radio frequencies, we could make this approximation. How do we know nga nata sa radio frequency if ma-satisfy na yung mga conditions? When omega times L is greater than R and when omega times C is equal to G. Pwede na ito ni i-substitute nga alpha o beta dito. Alpha is equal to R over 2 times characteristic impedance plus G times characteristic impedance over 2. And beta is equal to omega times square root of LC. So let's define some terms. Electrical length. I think ato na mentioned last time. Electrical length is the length of the transmission line well, the length of a transmission line, and it is in terms of wavelengths rather than in linear dimensions, rather than in meters or in feet, whatever. Use electrical length is in wavelengths. So how long is this particular transmission line? No, with the ingon, that's 1 lambda long or lambda over 2 long, 1.5 lambda long. So that's electrical length. So incident and reflected. Okay? So incident mo niyang forward, of course reflected is backward. This is the forward signal, forward voltage, forward current, forward power from the source to the load. And yung opposite reflected is the voltage, current, and power from the load to the source. So from kani source to load, kani load to source. Incident voltage and current are always in phase for a resistive characteristic impedance. Again, for resistive characteristic impedance, the incident voltage and current are always in phase with each other. So now suppose, okay, we have a source. Ito sa niya pag-drawing kanina ha. Ngayon ako siguro to. ZO and ZL. Normally, we only have two scenario sa yaning setup. Is either ZO is equal to ZL, or the characteristic impedance of the line is equal to the load, or not, no, equal to ZO. ZO and ZL are not equal. So when we say not equal, napagin ay tulo, no? Not only is it not equal, but it might be ZL is equal to, because ZO is a constant value, right? It's possible that ZL is equal to infinity or ZL is equal to 0. No? So this is when the line is short, short ni, right? Kung short circuit, kung ZL is 0 day kung short, kung open ni siya, no? Resistance is infinity kung open line man. And this is when the line is short. The load is short. Yeah. So we also heard from the video that the most ideal condition is when ZL is equal to ZO. This one. That is when maximum power transfer occurs. We've learned that from circuits 1. Transmission, in this situation, the transmission line is called a flat or non-resonant. Okay, wala may mag-resonate na signal. And no reflected waves exist. Okay? So tungod kay equal ang value sa characteristic impedance and load, walay signal na mobalik sa source. But for the 3 other situations, transmission line is called resonant and similarly act as an LC tank. Kadumdum mo sa mga isa sa mga description sa LC tank. Anong tank ang tawag? Diba? An LC tank will store energy infinitely. No? So wala mag-ideal. Konsuman ang mga wires na connected ani. Pero yes, the signal will just bounce back and forth between the capacitor and inductor. Malagyan ang sa akong pagdumdum, no? So it will store energy infinitely. Na bounce lang ang signal or ang energy, no? So somewhat similar ang mahitabo when ZL or the load is not equal in value with that of the characteristic impedance. So also it's possible that our ZL may also be a complex value. No? Samot na kung complex value. Hindi sila mag-equal. Not only does reflected waves not exist in equal value for load and characteristic impedance, standing waves does not also exist. But of course, standing waves are a product man of reflection, diba? So, tungtong na earlier na kita sa video kung sa itsura sa incident wave and sa reflected wave, and if i-add na to ilang mga amplitudes, that's the effect, no? The standing waves. Standing waves ang tawag because first nag-key ani nga term, nag-coin ani nga term. Sige siya, sense of humor. It's as if daw ga stand ang mga waves. Kung i-measure na siya sa oscilloscope, yan man ang atong makuha. Standing waves. Mga dos like the stand. No joke. So this is what we want. This is what's ideal when ZL is equal to ZO. So for the other conditions, when ZL is not equal to ZO, or when ZL is infinity, or when ZL is equal to 0, that is when sa kaning mga incidences, standing waves exist. Okay. Ano mo sa silong? Reflections and standing waves exist. So ZL is equal to infinity when the line is connected to an open circuit. No? So kung wire lang siya, na walay load na connect or anything, muna siya. Kung atong ibutangan og kanang i-short na to ang line sa end, ano siya, ZL is equal to 0 or short circuit na load. Okay. So standing wave ratio. Standing wave ratio together with the reflection coefficient are parameters that determine if tsada ba ang line. No? So we do want to have no reflections and minimal na standing wave ratio. So how will we measure standing wave ratio? So WR is equal to Vmax over Vmin. Okay. So Vmax over Vmin. Or also equal to the peak amplitude of the incident wave plus the peak amplitude of the reflected wave, VR, Vi plus VR over Vi minus VR. So if walay reflected wave, so this is 0, Vi divided by Vi equal to 1. So an SWR of 1 is what is ideal. This is silong sad. And SWR could also be measured using the characteristic impedance and the load. No? Okay. It might be medyo lisod ni siya i-measure practically. no? So SWR could be measured using ZL and ZO. How? By dividing lang, no? Dividing the ZO and ZL, or vice versa. So pareha siya as long as whichever is greater than 1. So there is no SWR whose value is less than 1. Dapat, no? Eh, kung less than 1, that's impossible, no? Wait ko lang sa kaninga equation. So whichever aning formula mag-yield o value greater than 1, ano sa itong gamitan? Panigapon, reflection coefficient is also a metric to determine how good the connection is, if not by standing waves or not, if not by reduction or not. So gamma is equal to VR over VI. But there is a relationship between gamma and SWR. Okay, again, should man i-measure. So ideally, when the line is matched, VR is equal to 0. So the ideal condition is when gamma is equal to 0. Kaya po dire, no? Worst case scenario is tapos sa silong, no? When gamma is equal to 1, meaning equal ang reflected ug incident wave, no? Meaning wala gyud lugar i-absorb ang load. Okay, kanang 1 man ang VR VI, or when SWR is infinity. We'd want to have our SWR closer to 1 as possible. So this is the relationship between gamma and SWR. If natay kani mas lalim na sa mapangita. So we could get the SWR. If you have the SWR, we could solve for the reflection coefficient. So these are the relationships between SWR and gamma. So kaniyo gingon, medyo lisod ng gini-imagine kung nakasulat lang. So if nakita na itong video previously, di na natin lisod imagine ang incident and reflected wave. So where is this standing wave, di ba? Kani sila. Standing waves. So asa man sila gikuha? They are measured by adding the peak values of the incident and the reflected. No? Peak values, di mag-matter ang polarity. No? So kung i-add ni, of course, 0, 0 dire. I-add na to ang kaninga peak. So it's as if na times 2. No? Times 2 ang value. That's why wala siya ang itsura sa standing waves. So where is Vmin now and Vmax? Vmin is this one, no? And Vmax is this one. Kani kung dili open or short ang atong load. But if our load now has a value but not equal to 0, I don't think 0 ang Vmin. No? Kasi lang, may minor lang na siya. Sama niya siya ng klase na load eh. 0 ang voltage or short. So I think short niya siya. Wala lang i-indicate. Pero sige lang, no? Ignore lang to akong mention ka lang. Okay, so that is where we measure the standing waves, no? The sum of the incident and the reflected waves. Notice na ang distance from Vmax to Vmax is 1/2 the wavelength. No? So timan-inan ninyo nidaan na observable na fact. Again, the distance between the maximum values is 1/2 wavelength. No? So let's say, for example, this one and this one right here. So the distance between this point to this point is 1/2 of the wavelength of the signal passing to the transmission line. Consequently, the distance between the minimum value and the maximum value is, of course, 1/4 wavelength. Appreciate nato iyang significance as we move further. So another term for Bmax is antinodes. Another term for Bmin is nodes. So the separation between node to node or antinode to antinode is 1/2 of the wavelength. And the separation between nodes to antinodes and vice versa is 1/4 wavelength. Standing wave ratio. So I think one itong nakakaganina. No? Standing waves naman siya ba? So, dili na ni siya kaning illustration now in front of us. Dili na ni siya reflected waves and incident waves. Standing waves na sila. No? So, walang i-withdraw or butangan siguro color ang voltage. So, voltage is kaning violet na lang siguro, no? Okay. So, ignoring lang ng sa likod, kanang current nga standing wave. So, ang voltage standing wave sa kaning illustration is kaning naka-violet. Okay? So, ignore lang sa ng current for a brief moment. So, if our line is terminated with an open circuit, no, wala tayo butang nga load, dili na to i-short, ang itsura sa standing waves is ingaani, no? At the very end yun sa transmission line, voltage is maximum. Okay. So doesn't this logically follow based po sa atong mga prior learnings before sa other subject? Diba? Kung open circuit, di ba yung voltage is equal to the source, right? Dumdum mo. For example, yung ani, open circuit man siya. What's equal to VO? Diba VS? So the same gapon here. Okay. If our transmission line is left open, max ang atong ma-measure nga standing wave sa very end is the maximum value. No? Bali siya sa current standing wave. Current standing wave is 0. Okay? Or the minimum value. Much like gapon of an open circuit, no, where current cannot pass through, so current is 0. Same here. Current is, or the value of the standing wave, the current standing wave at the open end of the transmission line is 0. Now, back ta sa atong learn regarding nodes and antinodes. Notice that so load na ni nga pan load na ni siya nga again nga part from here to here. notice that 1/2 wavelength away from the load is nagbalik ang value, no? Nagbalik ang value sa standing line, standing wave. Standing wave. The same gyapon sa current, no? 1/2 wavelength away from here to here is 0, no? Or minimum, I mean. And notice also, 1/4 wavelength away from the load is the minimum value for voltage, no? Diba? So, sa load mismo, no? Sa load mismo, we could measure a maximum value for voltage, yet 1/4 wavelength away, we measure a minimum value for voltage. The same gapon sa current. If minimum ang current standing wave sa load na part, 1/4 wavelength away, maximum. Also, VR is in phase with VI sa kanina kuan. And IR is 180 out of phase with II. So if value na to, no, if terminated siya at short, iyang response is mag-inverse lang sa kung terminated at open, no? In much the same way na kung mag-measure ta og current o voltage sa isa ka shorted na line, di ba? Sa shorted na line, di ba voltage is equal to 0, a short man. And current is maximum, right? So the same gapon dili. If our line is terminated with a short circuit, what we could measure what standing wave we could measure is voltage is minimum, diba? Voltage is minimum. 1/4 wavelength away from the load, voltage is maximum. Again, 1/4 wavelength away from the load, voltage is maximum. 1/2 wavelength away from the load, mag-repeat lang ang cycle. If sa load, voltage is minimum, 1/2 wavelength away, voltage is still minimum. And mag-continue na siya. So, bali sa current standing wave. At the shorted end, current is maximum. 1/4 wavelength away, 0. 1/2 wavelength away, bite na po siya og maximum. So voltage and current standing waves repeat every 1/2 cycle, 1/2 wavelength cycle, and goes from minimum to maximum and vice versa every 1/4 wavelength. So before I proceed, any questions? Kaya pa? Sablan pa? Are you guys awake? KG pa. Whole new world. Masyada gito sa video una. At least mag-visualize na to. Now, what if that will happen, no? What if ZO is not equal to ZL, no? Mga worst case scenarios lang man tong terminated at open and terminated at short. No? Mo tong mga worst case scenario and mga extreme conditions. But normally, normal noon nga incident is when ZO is just numerically not equal to the characteristic impedance is numerically not equal to the load. Samot na if ang atong load is a complex value. Most of the time, I can emphasize man yapon sa video. Ang load is complex value, meaning na siya imaginary na component.
Sir, na-mute ka, sir. Sir, na-mute ka, sir.
Hello, dunggan ako?
Yes, sir.
Ako nga part na undang
I think katong sa ningon ka nga mauto ang extremes na parts, sir.
di ay.
Uh,
Actually bitaw. Abi no gamino ang moato nga na-mute ko kay nag-make ko man joke with katugid nga time sad. Wala niyo nasabtan akong joke.
wala may kaapas, sir.
Timing yun. Bitaw kuan bala bitaw mo sila. Bitaw mo sila oy na-mute ka sir, na-mute ka kay joke naman ko ato. Tinod di ay. Sige, extreme conditions, no? Sige, wait lang. Ito ang joke. So, ako to, extreme condition. Extreme conditions siya kung ZL ay open o short. No? But most of the time, di man gina sila necessarily short to go open, but di lang yun match ang load o ang line, no? And more than that, ang load is a complex na value, no? So akong kuan is we want our line and our load to match, of course. Mo na nga atong gusto, because if match sila, walay reflections may tabo, no? Walay reflected wave. So timing na kayo ang atong topic karon, match and mismatch line. So how about you? Ana mo ika-match karong Monday? So base ng solution is na dire. Okay, ato mo lang solusyonan. Dili pala ka ang ka-match. So ato nang solusyonan dire, no? We'll try to find a solution on how to match our load to our line, at least, no? So wala tayo labot. Ang line ang load lang ang ato i-match. So there are two ways on how to match the load and the line. If ang atong load is simple na resistive na value, no, dili complex, no, wala siya imaginary nga component, I think naa diri nga akong kuan mo ni siya last na part sa akong notes, quarter wavelength transformer, no. So this is a solution on how to match the line and the load if the load is purely resistive, no? But of course, this doesn't normally happen, man. No, the load will always be a complex value. Pero mas ma-support lang ni siya ang atong ang concept, no, of how to match the line and the load, especially even if ang load is complex na value. So another solution on how to match the load and the line is to connect a piece of transmission line between the load and the line, no? So maragyan okay. So this is our line, no? This is our load. Our complex valued load. Na, hindi sila match, no? ZO is not equal to ZL. So what do? We connect a piece of transmission line somewhere, no? Somewhere between the line. So, imagine na lang akong glowing is 3D, no? Imagine akong glowing is 3D. So pwede ta magbutang og piece of transmission line that we technically call a stub. No? So matching stub. Magbutang ta og stub. Actually, dili anywhere giday, no? Yeah, positionally anywhere siya. But specifically, kinanglan nato i-compute kung how far siya sa load, no? So nanay specific length kung sa kalayo ang matching stub sa load para ma-match ang line and ang load. So mahulog ang matching stub is a parallel na circuit sa line, no? So malaging ana. So having that in mind, we take advantage of the input impedance of our transmission line. So the input impedance of a transmission line varies from 0 to infinity every quarter wavelength and can be purely resistive, can be inductive, and can be capacitive, depending on the distance from the termination or the load. So if naday tayo kuan piece of wire class, no? Piece of wire. So depende kung sa siya kataas. Again, depende kung sa siya kataas. Pwede siya pure nga conductor or resistor. Pwede siya mag-act as inductor or pwede po siya mag-act as capacitor, no? So amazing. So if our kuan, where is this measured here, no? So the input impedance, just like the input impedance of any device that we previously discussed, input impedance, is measured from here, no? Sa input na side. Okay. So again, this is terminated at open, meaning open line ni dire. Okay. So if our piece of wire or piece of stub is a full 1/2 wavelength long, it is like a resistor, no? So ako naman ang na-indicate dire. No? 1/2 wavelength away from the input, ang value is a resistance, no? And it is a maximum amount of resistance. Bali siya sa 1/4 wavelength away from the input. 1/4 wavelength away from the input. Here, minimum resistance. So the wire, the piece of stub, no, is resistive either 1/4 long siya or 1/2 long. So kung 1/2 long, a very large resistive value. Kung 1/4 long lang, a very small resistive nga value. So anywhere in between, no, any value between 0 to 1/4 wavelength long is inductive. Okay? And any value between 1/4 to 1/2 wavelength long, it is capacitive of increasing value, no? So if ang atong wire di ay, atong wire, iyang value, or iyang length, if ang length sa atong matching stub is anywhere between 1/4 to 1/2, iyang response is capacitive of increasing value. So before I go further, any question? Sabtan la? Malabitaw siya equivalent circuit, no? So ang atong wire, ato namang na set ganina pa lang na at high frequencies, our wire could be a complex na circuit, no? Complex RLC nga circuit with capacitances, inductances, and resistance and conductance. Pero if it is specifically 1/2 wavelength long, it's a pure resistive value. Even 1/4 wavelength long, resistive gyapon. Gamay lang nga value. If shorter siya than 1/4 wavelength, ang atong piece of wire kay marag inductor, no? Marag inductor. If taas-taas siya kaysa sa 1/4 wavelength pero less than 1/2 wavelength, na siya capacitor. And the inverse is true kung ang atong line is terminated at short. No? So the same magyapon ang idea. No? Kung short circuit ang atong kuan, just like sa akong example earlier, gigi-drawing, di ba? Katong pwede nga kuan. If this is our line, if this is our load, yung butang taog as if matching stub here, no? Nga short. No? Connected man ang duha. So short ni siya nga matching stub. So yung reaction ani is the same ani ikaduha nga kuan. Ikaduha nga graph. So 1/4 wavelength away from the input is maximum resistance. 1/2 wavelength away, minimum resistance. If yung value is somewhere in between 0 to 1/4 capacitive, 1/4 to 1/2 inductive. So, na sa graph. So there is a reversal of value every 1/4 wavelength, and there is a repeat of value every 1/2 wavelength. So if i-extend pa nato ni, no? If ang atong matching stub is longer than 1/2 wavelength, no? Example, atong matching stub is this long. So unsa ang pilay value at this point? The same siya kung pilang sobra dire. The same siya sa value niya at this point. Because again, the input impedance, value of the input impedance repeats every 1/2 wavelength. Reversal every 1/4. No? So again, the first way to match loads is to use a quarter wavelength transformer. So what is a quarter wavelength transformer? Unlike sa stub, i-place nimo in parallel sa load and sa line, a quarter wavelength transformer is i-insert siya in between the line and the load. So muna ang transformer. Diba? Iyahang length is 1/4, exactly 1/4 wavelength long. No? So you do not need to compute for the value of the length. The 1/4 wavelength yun na siya. But how much is the value? How much is the characteristic impedance of our quarter wavelength transformer? We can use this formula. No? For example, lugar tayo line nga 20 ohms and natay load na 50 ohms. So, pila man na siya. Pila dapat ang matching stub na ang quarter wavelength transformer. So, 31.6 ang input impedance sa atong quarter wavelength transformer. 31.6 ohms. So, this first solution is if the load is purely resistive. No? If dili purely resistive, meaning complex value, medyo complicated ba ang pamaagi, mo to siya mo to siya solution matching stub. Pero even though simplistic ang solution, no, we just insert a piece of transmission line anywhere sa span sa line. Pero the determination of how long, no, is the matching stub and where yung position sa nato siya ibutang, diyan na din mo sulod ang Smith chart, which is a very, very complex na process. No? Hindi na ito makover this afternoon. Itaas-taas yun siya. So the next slide is a summary of the equivalent circuits of different lengths of transmission line. No? So kani, this is 1/4 wavelength long. Okay, so 1/4 ni tanan. Wala noon siya nagamit o nagbuhat og graph just like this one. But giset na niya daan nga 1/4 wavelength. So a 1/4 wavelength na matching stub, 1/4 wavelength na matching stub nga short, yung equivalent circuit is resistive and maximum. Sakto ba to? The same ba sa to one? Short nga 1/4 wavelength, short nga 1/4 wavelength, maximum, no? Sakto dila. Mag-measure tag input impedance here, only 1/4 wavelength nga short, maximum resistance. If open, minimum na resistance. Pero even if resistive iyahang value, iyang equivalent circuit is inductor and capacitor. Mag-cancel out man na ilahang mga reactances no siguro long term, no? So so a real resistive value na lang mabilin. If less than 1/4, if less than 1/4, then short, inductive. No? Ako siguro to measured from the output, siguro ni input impedance kaning bali man siya sa kanila ko nga ilang kay dili man sila dapat mag go against each other, no? Isa lang akong gigikanan ani nga source. Input impedance man, no? Input impedance nga short is inductive. Na siguro na kuan, no? Na siguro ay part doing ako na miss out. Basta kay or sa yup na eh. Pero sige lang, anyway, di na kayo na mag-matter. Pwede lang natin na ma-check anytime yun, no? Mas accurate no ng Smith chart yun ani, no? Maybe ay part nga inaccurate dili sa kanina slide. Pero the point is, lahi-lahi ilahang circuit equivalents, no? At different lengths for our matching stub, no? Pwede 1/4 wavelength long, pwede less than that, pwede more than that. So muna ilahang mga equivalent circuit, no? Tingnan ko lang yung i-check. Pero I think both of these are quantum said, no? Na lang siguro part din akong na overlook. So anyway, another thing to remember is this is a summary of all equivalent circuits. But in terms of practice, dili advisable ning mga open-ended na mga matching stub. Why? Because they might act as their own antennas, no? So na-defeat ang purpose. So instead nga transmission line lang nakadungag tag atong own nga nahimo siya iyang kaugalingon nga antena kung open circuit, no? May tendency nga mag-radiate siya electromagnetic signal kung open line. So naara somewhere aning tulo ang mga solution, no? Which is good na magyapon. Why? If more than 1/4 wavelength na short, ano yung capacitive? Kung less than 1/4, inductive. Kung exactly 1/4, resistive. So, nalagyapon itong mga possible choices sa natulo. So, iwas daw tao gamit o open-ended nga matching stub. Okay? Kung na-check again ha, kung asa dapit dire ang kung na-overlook or nabagyo'y inaccurate sa akong drawing. Pero kanigi based sa mga gyapon ako ni sa one. Same source as this one. Right. Any questions so far? Processing pa. Okay lang. Pwede lang yun watch again. No? So, let's try to solve some examples problems. Nga nang kayo po sa yun, no? Trivial. Number 1, compute the wavelength in meters at frequency of 350. Dali naman no? Wavelength is C over F, no? A coaxial cable has capacitance of 30 and inductance of 78. What is the characteristic impedance? So, formula aning number 3. So, may siguro itong extremely high frequency. So, L over C. It's number 3. DO is equal to square root of L over C. Wait lang sa class, Okay, so the answer ani, L over C. Square root of 78 nano over 30 pico. 50. I like that. 51 ohms. So, nagis sa mga yan ang value ang characteristic impedance, mga below 100. Velocity factor of coaxial cable with dielectric constant of 2.5. So, formula ani. Velocity of propagation is equal to velocity factor is equal to 1 over the electric constant naman. Medyo trivial naman 0.63. So kanina dayon, ang velocity factor dayon ang i-multiply sa speed of light para makuha ang actual nga velocity of propagation. So the signal travels 0.63 times the speed of light. No? Mas slow siya, of course. Ang ideal na velocity factor is 1 man. No? So, tungkol kay na dielectric, 0.63 na siya. Yung mga challenging din. 15, oh. 52 ohm coaxial cable has a 36 ohm antenna load. That's the SWR. No, it's either 52 over 36 or 36 over 52. So, mas nakuha ng 52 to 36. 52 divided by 36 on eh. SWR is 1.44. If matcha, well, SWR is 1. No? Moment to ideal, right? SWR is 1. Maximum voltage is 170 and minimum is 80. Calculate the SWR and reflection coefficient. Kaya na. Okay, formula na. What are the reflection coefficient and SWR open and shorted? Itong worst case scenario, wala. 1 in infinity. Wala. Yung mga worst case scenarios, one ang open and short. No? So, reflection coefficient is 1. And SWR is infinity. One ang mga worst case scenarios. Ayan, kada ni sila. Kada ni nga mga example, mga next meeting sila ito ang cover. Smith chart. Okay, so di lang si tataman ka ron. No? Aside from the Smith chart, naumana na to ang mga topics na to for this chapter.